Oh my god. Oh,
We are meeting from 3, right?
mm-mm.
But since I is not shutting
It's okay. Just wait.
anything.
If he terminate, then we can email him. Maybe he went to toilet also. I feel so tired. I had bad dream yesterday. Last night.
What?
I have a bad nightmare.
Oh, bad day for you. I am also feeling tired today.
Because you just come back from Tokyo.
Yeah,
Mm.
I walked a lot for the last 4 days. Usually, I'm not so much used to walking so much.
Mm.
I'm feeling tired.
Yeah. You can go back after meeting.
Yeah, yeah.
I
So,
also want to go back. I have so many things I want to do, but I don't know. I just don't feel that I want to do anything today.
yeah, it happens some days.
Maybe since I forgot.
But that is very rare. I haven't seen anything. Have you seen anything?
Huh?
Sensei forgetting?
Yes.
Oh, really?
Yeah. Ah, Let me email him.
Yeah.
Okay, sorry, I misunderstood. You will come to my office, but no, online. Okay.
Okay.
Okay, is everyone Okay, let's start. So, Zafira-san,
はい。
could you explain?
Okay, Sensei, can you see my screen? Hello? Sensei?
Okay.
Okay. Okay, I will start. So I already run the case study. So we have 100 to 10%, but I just run for 25 for this one. So this is for 25, the story tree. So the case one is elastic, case two non-linear and elastic, and then case three elastic non-linear, and then case four non-linear means that we have two them put together. So this is 25%. So you can see that case one and case two have a small story because the beam is a bit stiff compared to the one case four and case three. Case four we have the elastic and metallic damper. And this one is for the accelerations, and with different percentage of force ratio, it doesn't have much difference. And as we can see, for example, 50%, the story drift in case 4, the one that we together with the damper, actually already exceeded 1.28 centimeter, the limit for the our story drift.
Okay. One moment. I would like to say, because there are people who don't know the background,
Okay.
so I will explain a little bit.
Okay.
So there are 4 cases. So we are analyzing the building coupling beam. So this is a coupling wall. Okay, this is a wall. And between there are coupling beam. Okay. So first case is the coupling beam actually has a bending spring append and a shear spring in the middle. So this is a coupling beam. So this one we assume over yielding of steel. So we call metallic damper. Okay, so this is metallic damper. And this one we assume to viscoelastic. So this is shear force. So this one is moment, and the Q is shear force and rotation. And the first one, we assume elastic. So yielding of two springs intentionally very large. Maybe you should put the kilonewton here. Unit.
Okay.
Right? And second case is we assume yielding for metallic damper. Actually, the metallic damper yielding at both ends is, we assume, equivalent to metallic damper in the middle, right? Because the shear force and the moment is related each other. So anyway, this is a bending spring assume yielding. So 1,500, it is how much percent for this one?
This is 100%. The Q is 100
The Q is 100 kilonewton.
So times
1.5 meter.
So this is a case of 100%.
Yes.
Okay. But in this case, it's not yielding 100%, maybe. Too strong.
But this is one input data, but I also run for until 25%.
Okay. So the minimum is 25%.
Yes.
So you change percentage. Yielding.
Yes.
And third case is only viscoelastic damper. So in this case, you change percentage of viscoelastic.
Yes. I also change. This is 100%. And if we go 25, it will be reduced.
Oh, okay. And the last one is a combination of two dampers.
Yes.
Okay?
Yes.
And could you go to the next? So in this case, 25% for which one is 25%?
Okay.
Both of them, Sensei.
So
we have blue one is case 1, and the orange one case 2.
So case 3 and case 4.
Case 3 we have metallic and viscoelastic. But the metallic is elastic.
But for
case 4 we have metallic and visco. So the storage drift is same for case 3 and case 4.
Okay, so case 3 viscoelastic and metallic.
Viscoelastic.
Only viscoelastic.
Yes.
Because metallic damper doesn't yield for case 3. No, case 4. It doesn't yield, so the result is the same.
Okay.
Case 1 is elastic.
Yes,
Elastic looks small deformation, but over 1 centimeter. And case 2 looks very good. So case 2 is metallic damper. And how high?
10 stories, Sensei.
No, story height.
Inter-story height. The inter-story is 3.2. The total is 32 meter.
3.2.
Yes.
So 3.2
times.
And if you divide 1/200,
250 is 1.28
centimeter.
1.2. So 1.28?
Yes, centimeter.
So maybe you should draw the line.
Actually, I have other graph to show you later.
Oh, okay.
And this one?
And this
3 earthquakes.
Yes, I compare 3 earthquake.
And this is the accelerations.
But the eccentric Kobe is also artificial.
Yes.
You just use eccentric phase and Kobe
I
phase.
use the artificial central artificial Kobe.
Yeah.
And what is this one?
Which
Random phase?
Random phase 120 seconds. Random phase.
Maybe you should put
random phase.
Okay. Okay. Case 3 and case 4 are all equal. Okay. Could you?
Okay. And then I also run for
the shape is
the shape is not much difference, but the displacement a little bit reduced compared when the percentage increase. Also, but after
Percentage increase in metallic damper yielding, but not so much. So it's very close to elastic result, right?
and after
50%, the difference is not that much difference. So for example, this is like 1.5. If we go to
100%,
100 is also almost near 1.5 centimeter.
So you mean viscous damper, even you increase viscous damper, the result doesn't change.
Yes. Okay. And then I try to optimize the locations of the
damper
because here, for example, 100%, the location of damper is from level 1 until level 10.
Okay, and then
from these a few papers, we can know that the bottom have a large shear force, and also at the top, actually it doesn't displace. It doesn't need damper at the top and the bottom. So what I did is I replaced
the bottom from level
1 until level 4 with metallic for steel beam, and also at level 8 and until level 10
for steel beam.
And for in between 5 to 7, I use viscoelastic plus metallic damper. And after that, the storage drift
can be reduced less than the
limit. And if you can see the gray lines inside, the gray line is from steel beam.
So if we have
a stiff beam
at the
bottom, we can reduce at the bottom.
And also at the top, we doesn't need a lot of rotation,
so we can just replace by steel beam instead of using metallic damper and viscoelastic.
Sorry, I understand.
If we can see from the previous result, all the metallic damper and viscoelastic
here, they have a larger storage
drift. Even though the percentage is increasing,
it still exceeded the limit. So what I did is I tried to optimize the location of metallic damper. Not every story have metallic and viscoelastic. Only at level 5, 6, and 7. And others are using steel beam.
Would you show me, the formation of the coupling beam along the height?
Okay.
You are just plotting
storage. This is the deformation for viscoelastic. For the damper, this one at level 5, level 6, and level 7.
What is the level? What does it mean? Story?
Yeah.
Huh?
The level 5, level 6, and level 7.
You mean the story?
Yeah,
the story height.
Not story height. So
if I can
position the damper
in the middle, only the middle story, I can reduce the storage drift.
Also this for L central. And this one is for Kobe. So only the L central have a bigger storage drift. So what I did is I replaced the bottom beam with the bigger size. So I increased the stiffness of the steel beam. So I can reduce the inter-storage drift. And this is the hysteresis figure from the damper at level 5, 6, and 7. So for this one, the metal doesn't yield for these three cases. But for this one, after I replace the bottom steel with the larger beam, the metallic damper start to yield.
But you also put the viscous
Yes.
damper in the lower story.
Lower story, no. Lower story only steel beam.
Lower story only steel beam.
And also upper story. Only the middle one, we have metallic and viscoelastic.
What is the theory behind?
I haven't find the theory, but I use steel beam to reduce displacement in the beam. So I let the intermediate story to have more to displace, like for example like this research paper. They only put in.
But if you put steel damper all along the height, it is the best performance.
Yes, like this. If we put the gray color one, it's the steel beam. So this is the story drift. But if we put the damper in the middle, if we compare here, so it have less story drift compared to the steel beam. So this is the original one, case 4. And then replace only the middle one have damper. So it's much more better compared to we use all steel in the all story height.
Could you explain what is the difference, this green one and gray one? What is the difference?
The green one is the optimum that I change only in the middle story from level 5, 6, and 7 have damper. Like level 1 until 4 is the steel beam, and also 8 until 10 is the steel beam.
Steel beam means metallic damper.
No. Steel beam is just steel beam. Steel beam is just it's not metallic. Elastic. Steel beam. Normal steel beam. 600 by 200. The size.
So no yielding. Yielding or no yielding. Elastic. This one.
For the gray color.
Yeah.
Maybe I can open the Stereo 3D. And OPD. So. So let's go level 1. So this is steel beam.
Could you show me the property of a beam?
Okay.
B2.
B2 here.
Could you click?
This is from data beam.
So this is 100%.
Data beam for metallic. Yes, 100%.
100%.
Okay. And then for example,
so it's elastic. So no energy dissipation.
Only in the one with damper sensing. Level here, level 5 until 7. So this is the history 6.
Could you show me the acceleration of this?
This one? Acceleration is here. Yes.
The acceleration for optimum case. It is even larger than before.
Yeah.
So it's not good. you can reduce deformation, but you increase acceleration.
Because it's too stiff.
Last time I asked you to, so I was thinking to combine two damper,
Yes.
right?
Yes.
And back to, for example, 25%.
25%.
This one?
Okay. Oh, and let's see. Acceleration after 25%. No, not acceleration.
The story drift?
The story drift. Okay. So this is a viscoelastic damper.
Plus metallic sensor.
No. It is a viscoelastic, case 3 and 4. No?
Yeah,
viscoelastic.
Viscoelastic.
Okay.
Right? So this is viscoelastic. Well, I just to say, right, to V. Okay? V. And this is metallic. So it looks metallic, it's very good. Because it's less than 1 centimeter. Okay, so viscoelastic, more than 1.5 centimeter. So you want to reduce it. Okay? And case 3 and 4, same result, because the metallic damper does yield. Okay. So case 4. So it must be metallic damper plus viscoelastic damper, case 4.
Yes.
But the metallic damper is not yielding, so it is the same as case 3. So I suggest to reduce strength of metallic damper. So two damper both yielding, I mean both dissipate energy. And did you try?
Yes, I tried. But the ductility for when the metallic damper is very small, the metallic damper broken. And for example, let me try here.
No.
Case 4. Okay. And then so we have steel and viscoelastic.
Yeah.
And properties. For example, for metallic, we take the small number, 25%.
So 25%. Okay.
25% is
the 375 kilonewton per meter. And then this viscoelastic, the largest one, let's say we can
50%
and take 11.4 and 0.466.
This is 50%
viscoelastic.
Okay. Then, could you check
level 1?
Okay. Yeah. Okay, so it starts yielding a little bit.
Yes, but it doesn't like go circle. It's like going. It's a bit weird.
Oh, it's very weird.
And also viscoelastic deform very weird.
So weird.
なんかおかしいな。Really? これは何かおかしいね。Could you check option analysis?
Okay.
Options.
Analysis. Dynamic.
Is that? It's 20. Okay. Could you change another earthquake?
Another. Okay. Sorry.
Okay.
なんかおかしいね。It's strange. Really? Okay. Could you send me this model?
Okay.
I will check.
I will
I will
also send you the optimum one. Yes. And because Sensei, like previous research also say that viscoelastic damper, it doesn't have to go all along the height. Usually it's only put in the middle story. So that's why I just tried the theory for the model.
Oh, really? Real example, they put only middle story?
Yes.
Are you sure?
Yeah, this is the from the Toronto
project in
so they put from here to here.
Yes.
I can. There is yellow part.
And
that's
Okay. Yeah, because they want to reduce higher mode, second mode maybe. But your building is only 10 story.
Next step, Sensei, maybe Sarah-san can try 15 story. I try 20 story.
I try it and we can compare the result.
But this part is, for example, going down. No. If you apply earthquake from right to left, this part will go up and this part up. But in the bottom, almost zero deformation, right? So actually, the difference between two walls, I mean vertical difference, is getting larger along the height. You understand?
Yes.
Two walls, and you are pushing from this way. This part will go up and this part will go down.
Yes.
And so this shear deformation along the height is getting larger.
Yes.
So I think it's very effective damper in top stories.
I have one question.
Yeah.
Because viscoelastic damper, they move it's very flexible. So if we put on the top story, it will have more deformation. If we give deformation instead of
more deformation of reduced deformation.
Well, it's also depend on the flexibility of wall.
I see.
Maybe upper part will move like a two wall. I mean, like one. なんていうのかな。So this part is just a rigid movement, rotation. So no difference between two walls. Yeah, could you check vertical deformation of, I mean, shear deformation of coupling beam along the height?
Okay, Sensei.
will check.
Do you understand what I mean?
You want to see the shape when they have higher shape, they also have high deformation on the top, right?
、Yeah, so I want to check shear deformation of coupling beam.
Okay.
And along the height.
Okay, sensei. You mean you want this kind of like beam shear, right? This
shear forces. I want to see the shear deformation.
Okay, shear deformation
along the height.
Okay, sensei. That's all for today, sensei. Thank you so much.
It's not good if you have yielding of metallic damper, viscous damper together.
This one?
I mean, the response is strange.
You mean in the Stellar 3D?
Yeah. This one is strange without something wrong.
How about this one, sensei?
This one is only metallic damper. No, viscoelastic.
No, sensei. This one is viscoelastic plus metallic together.
But you are plotting which level? 5, 6.
5, 6. Only 5, 6, 7. Yes.
そっか。そう。そうなんだ。So you have both
Yes.
spring
Yes. And another thing I forgot to mention. This one, since after optimization, I tried different percentage from 25 to 100. It doesn't have much difference.
Change, I mean, 25% of what?
Viscoelastic and metallic. The force ratio.
Why?
Maybe it's just 3 level of tempo. That's why it doesn't change so much.
Could you go back?
Okay.
And you put the viscoelastic damper for only middle story.
Yes, level 5, 6, 7. Maybe that's why the storage doesn't change so much.
Could you go back your slide?
This one?
No, from the beginning.
From the beginning? From here?
25%.
25%. Okay.
So this is only viscoelastic, right?
Yes.
Case 3.
Yes.
And could you show me 50%?
Okay.
It doesn't change much. Okay, how about 75? Almost.
This is 100.
So. Why? So this is a case you put viscoelastic all levels,
yes,
right?
Yes.
And you change, okay, yeah, you change K both.
Yes.
なんでだろうな。Could you go back to 25% again?
Okay.
So this is elastic.
Yes.
It's elastic.
Yes.
This elastic. So.
For random phase, the difference is not much, but if you can see asymptote here, this have a bit different. This is almost 2, but here is that 1.5 for Kobe. Sorry.
So in the R square also. How about 75 or 100%?
75 is less than 1.5. And it's reducing.
Okay, so how about the case 2? Could you show me 25%? So case 2 is this one, right?
Yes.
And how about 50%?
50%.
Case 2. It's reducing. Okay. Okay. Yeah, I understand. Yeah. Okay. Well, optimum damper location. The idea is interesting. You need some theory.
Yes.
Yeah.
I'm looking for it.
Or you make some different cases. One case is you put the same damper, all the levels, and one case is you arrange viscoelastic damper only middle story, like this. Another one might be viscoelastic damper top and bottom and the middle story metallic damper, for example.
Okay.
So, and you can compare the result. Okay. And you must write paper for JCAS.
Yes.
When is the deadline?
August.
You still have 1 month. 1 month.
Yes.
Okay. Yeah. So let's discuss more.
Okay, sensei.
And send me the file again. I will check.
Okay, sensei.
Okay.
Thank you.
But it's getting interesting.
Okay, sensei.
Yeah. So, we must start discussion about displacement-based design. Okay. And our target is story depth is 150. But maybe we should also discuss reducing acceleration.
Okay.
But from your result, you can success to reduce displacement. But on the other hand, you increase acceleration. So what is the acceleration? Story drift is 100, 200, 1 over 200. So we must consider kind of criteria for acceleration. One moment. なんだっけDo you know Michelle from Malaysia?
Yes. I heard his name before.
Yeah, she in thesis. I remember she discussed about the response criteria, both for this drift and acceleration, both. Let me check. I will share my screen. No, not the 違うな。How many years ago? ちょっと待って。何もしたかな。マトパトシア。じゃあ、あれ、誰だアンネさん。Yeah. So in Anne, I will show you her master thesis. Okay? It's a real-time seismic monitoring evaluation system. And paper, there is a kind of criteria. Oh, no. Okay. Yeah. So in this case, it's a moment resisting frame. So no shear wall. So story 100 is a kind of how to say yielding criteria, but the danger is 1/75, and the 1/150 maybe it's a criteria. I mean, less than this we can say safe. 250, maybe less than 250 we can say safe. But if it reach 500, we will say warning. And 1G, 1000 car, we can say danger. Maybe we can use this acceleration criteria. And this is not her original. It is a Japan structural, what is the abbreviation? JASCA. It's a Japan Society of Construction Agency or something like this. But they present so maybe you can use this criteria for acceleration. Okay. But the story drift have a shear wall, so I recommend this part. Warning might be 150, 1/250 instead of 100 to 100. Okay. Yeah.
Okay, Thank you so much.
Yeah. Oh, Sara-san?
はい。
Sara-san, I cannot hear your voice.
Okay.
Okay.
Okay. Now I'm gonna talk about experimental validation of viscoelastic coupling in terms of the enhanced dynamic performance of high-rise buildings. It was written by Michel Montgomery and Konstantin Christopoulos. And first, introduction. This paper describes the extensive experimental program that was carried on the small scale viscoelastic damper at the University of Toronto structure growth testing facilities for achieving enhanced dynamic wind and earthquake performance of the high-rise buildings. This paper's proposed is the small-scale viscoelastic test with the characterize the viscoelastic material this for realistic loading condition of high-rise buildings for the range of the strain and the frequencies.
One moment.
Okay.
I noticed this part is connected, right?
Yes.
Zakira-san.
Yes.
So this part is connected.
Yes.
So two coupling wall actually
Doesn't move.
at the top.
Okay.
So it means this part is connected and this part is connected. That's why the deformation concentrated in the middle.
So if we can restrain top and bottom, it will be good.
I don't know.
Okay, we have to try the case and we can see the different performance.
No. Usually we put separate to coupling wall. Otherwise, we cannot how to say, the advantage is when earthquake happens, horizontal load, this part is go up and this part is go down. So we can expect a big deformation in coupling beams. So we can use this big deformation to dissipate energy.
Okay.
But if you combine, put together as a top story, somehow you reduce this advantage. I don't know why they put two walls together. They connect. I don't know. Because it's very high-rise story. So they don't like a big difference left and right. Maybe. But your building is only 10 story. So if you connect the top, almost zero deformation in coupling beam.
Understand.
Okay. Please continue.
Okay. Viscoelastic damper configurations were capacity designed to ensure the tactile and the predictable performance at land in the domains. And next one is intended performance of viscoelastic dampers for wind and earthquake loading. It's designed to provide the performance improvements of overall ranges of wind earthquake loading. For the static wind loading, the viscoelastic frequency dependency must be considered as the static stiffness of the viscoelastic material is significantly lower than dynamic stiffness. For above the seismic loading, the strain amplitudes are larger than the wind loading, and the duration period is shorter than the wind loading. And it characterized by the fundamentals of the vibration plus the contribution of the higher modes of the vibration that are at higher frequencies, but the deformation amplitudes is lower. For this, during extreme seismic loading, a tactile force limiting fuse mechanism is mechanism is introduced in the series with the scholastic material, such that the fuses activate the limit forces transferred to the concrete wall. And to prevent the tearing of the viscoelastic material. So through the careful fuse detailing, and if needed, the inclusion of lock-up mechanism, it is possible to achieve substational shear deformation as a combination of viscoelastic material, viscoelastic deformation, and the fuse element plastic deformations. After extreme quick, if it is necessary, the damper can easily be inspected and repaired, or easily replace it. And based on the damper manufacturer were suggested and extensive material tests, the viscoelastic material strain limit was set as 100% and 105% for series level, and with ultimate level windstorm. It's between that response during windstorm are between frequencies is 0.1 and 0.2 Hz. For about design strain limit, it was set as 150% and 250% for service level earthquake and design basic earthquake. In additional an strain limit of 400%, it was set for the maximum credible earthquake.
So one moment. So Zafira-san,
Yes, sensei.
again,
Hi.
how much shear deformation? For example, 100% here. This one.
You mean in kilonewton?
No. How much centimeter?
How much centimeter?
No.
100%.
So it means viscoelastic. It's a kind of bar, right?
Yes.
And it will deform by shear. Yeah, shear force. So this is a thickness. how much thickness of viscoelastic material?
One layer is 5 mm.
5 millimeter.
Yes. But the total is depend on how much percentage that we design. For example, let me open the file. So for example, 100%, we have each layer is 5 mm. So we have 5 layers. So we have 5 layers. It's mean 25 mm.
25 mm.
For 100%.
So it means 2.5, 25 millimeter shear deformation is 100%. Okay. So 400% means multiply 4. So 100 millimeter, 10 centimeter. And from your stellar 3D analysis, please check how much
shear deformation. DX. DX. In Stellar 3D, SDX is for story drift. So DX is
no, not the story drift. I'm talking about the shear deformation of spring. So you get the spring deformation, maybe max beam.
Okay.
Yeah, you have a shear force and shear deformation. I don't know.
Okay,
but I think so. Yeah.
I will check.
And please check if this is less than this design limit or not.
Okay, sensei.
Okay, Sarah-san, please continue.
Okay. And so it is viscoelastic damper test, scope and the overall. First of all, this is description of the test specimen. The dampers consist of 4 layers of 150 millimeter viscoelastic ISD 111H, and it had 5 millimeter and 10 millimeter thick viscoelastic material. And however, extensive test data is available for ISD 109, ISD 110, ISD 111 compounds. ISD 111, it is a higher stiffness and better durability and less temperature dependency than the previous compounds. And next one is tested up. For about a picture in here, 150 millimeter and 5 or 10 millimeter thickness and 4 layers viscoelastic damper in here. And it is a handheld contact thermometer was used to measure the temperature of the viscoelastic material at the exposed surface.
This is very good picture. So there are 1, 2, 3, 4 layers. I mean, of visco materials. So, Zafira-san, you said 5?
Yes, I see.
So 100%
yes,
is
yeah.
So it means 25 means, but you cannot. So 5 or 3, 2, maybe up to 1. I don't know.
For 10% is 1. Yeah, you are correct.
Okay, so you cannot, I mean, control by 75 or 50. So if this is 100%, it should be 80%, 60, 40, and 20% maybe. Is that correct?
Actually, I just use 10%, 75, 50, 25. But the number
is
is 5, 4, 3, 2, 1.
Like
I think it's
like
round up.
But you use the same material, right?
Yes, I see.
Just changing the number of layers.
Yes.
Yeah. So if you use the same layer, 5 layers 100%, 4 layers is 80%, right?
Okay.
It cannot be 75.
Okay,
Sensei.
Yeah, thinking about the real arrangement of the this material. Okay. Okay, Sarah-san, please continue.
Okay, for about see picture in here, the specimen with the 10 millimeter viscoelastic layer at the shear strain of 150%. And after that, for about experimental result of the viscoelastic layer test, this formula to define the strain, stress, and the strain relationship of viscoelastic material under the harmonic loading. And this one is P is stress, this one is strain, and this one is strain rate. And this next formula is the energy dissipation capacity of the viscoelastic material. This is a loss factor in this shear loss models. Both shear loss model and the shear storage model are functions of the frequency, temperature, and the strain amplitude for a given historic cycle. And the first one is frequency dependency. A picture showing the shear strain response of the 5 millimeter thick specimens subjected to the sinusoidal loading with the constant strain amplitude. Strain amplitude is a constant. It was 50%, and at the frequencies of 0.1, 0.2, and 0.3 has 4 of the 10 and 10, 5, and 3.336 seconds, respectively. This strain amplitude 50% that was in black spots. And from this viscoelastic material temperature to the start of the test are reported considering the viscoelastic material property dependency on both the first temperature and the increase of temperature during dynamic loading. Loading and yes.
That's all?
Yes.
Okay. Very good. So this material property largely depend on the temperature. And also frequency. It's very complicated.
And shear storage models and the loss factor graph increase ascension frequency.
Shear modulus and the loss factor. Yeah, because it's velocity dependent, so yeah. But even same frequency, temperature, also affect. Okay.
Next one is strain dependency. Frequency is a constant. It was 0.2 Hz. At this amplitude, 50, 100, 100, 50, 100, 150, and is 200%. In here is wind loading, and one in 10 year and one in 50 year. It is meaning is if it was 1 in 50 year, it would be 2% chance that it occurred. And the shear storage models marginally decreases with the increasing strain amplitude. And shear storage models decrease when shear storage models was decreased, strain amplitude was increasing. And the loss factor is not significantly dependent on the strain amplitude. Viscoelastic material properties can be considered strain independent for a given temperature and the frequency from this.
Okay.
And for about internal temperature dependency, the shear strain response for 2 hours and strain amplitude 50% frequency is 0.1 Hz and 0.1 Hz. A picture is 0.1 and B picture is 0.2 strain response. At the beginning of the test, the increase in the temperature of the viscoelastic material is directly related to the rate of self-heating of the viscoelastic material alone, and the middle of the test when the viscoelastic material temperature reaches steady state, the heat transfer is defined by the rate of self-heating and by the conduction and the convection of the heat between steady plate, the viscoelastic material and the surrounding environment.
So I just
So self-heating may not be, may not influence so much. It says only
I did the thing that he asked me to do.
less than 2 degrees.
Like this one, like all the way have viscoelastic. And then like the deformation is very big because you know when you know viscoelastic it can deform.
So it didn't increase beyond the 2 degrees.
Which one?
So we can choose the single average temperature
1.5 centimeter.
Yeah.
for you.
But the limit is actually 1.28 here.
From this viscoelastic material property summary,
It's not small.
viscoelastic material
1.5 centimeter. Or interstory.
property depends over a range of extension
It's big.
frequency, strain amplitude, and the internal viscoelastic material temperature.
How much is the story do? If you divide 1.5
It was the first harmonic cycle at 1 and 2 hours, and for the 5 nanometer thick
Yes.
specimen, and the results are calculated at the natural frequency that was
Small.
between
maybe because of
0.1 to 0.2 Hz
shear wall.
at a strain amplitude at 50%.
And then I propose because like I know in
And
upper wall at the bottom it's very lush.
the material
And
properties,
even for this example, they use big
shear storage models, and the loss
and then
factor were very stable and predictable
cases,
for
this
the
is real building.
targeted service
They just put in the middle.
service
So I
and the
just try
earthquake. From this,
eliminate
the large
all
temperature
I only put in the
depends
middle
that has previously been
reduce from the
reported
yellow
for
to green.
actual viscoelastic dampers
and
made
the
of
green
the
ones,
ISP
steel
110
beam. Every story
material
steel
for
beam.
the low-rise building
Actually,
seismic
steel
Green is
application.
steel and gray is.
Gray is
So,
steel.
Oh, gray
it
is
is
steel.
not
Green is
expected
Green is
for
the
only
optimum.
wind or
Yeah,
earthquake
only
loading high-rise building.
Right.
Just
And
only
then he asked me, what
ISP
is the theory behind this?
107.
Experience.
It is most
I know that because I tried.
most
I just try an error. Unless I just put beam like steel beam and other top story
Have to
is
say.
velour.
Yeah, it is very stable.
I think the trip is still big at the
ISP
top, and then I try to
111.
restrain the top, and it reduced.
But which aspect?
Okay.
It's
This
ISD
is random
110
phase.
material.
This is central, and this is
Is
cold.
this the same material
And then
for
you know,
this
central is
one?
over the limit.
I think
right?
it is not
And then
same.
I increase
Not
the
same.
Yeah.
bottom
Mm.
with the bottom
In this
beam, and it can reduce
test,
more.
this material is
Because
ISP
I think in the
111,
bottom,
but this is
if I
most
increase the
very
beam,
stable
it can
for high
absorb
rise.
more shear.
But
Then why
in
you
this is the
provide
110 is
Because
not
I just said to him,
suitable for high rise
it's
building.
not only temperature, it's
It is
everything
just
about viscoelastic material.
Low rise in
Viscoelastic
seismic
damper.
application.
Okay.
Actually, this week I didn't have time to teach her, and I
Yeah,
also
so-
cannot ask her to do
Okay.
Stera 3D because since it's
Very good.
do,
Mm.
just you study by yourself, and then whatever you study, you present to sensei.
So, the damper is based on this study, right?
Yes.
But you also found viscoelastic damper from Japanese company.
Yes.
Eco.
The one that Majima-san recommended.
Yeah. Do you have any catalog or similar information from?
Not yet, sensei. Only that catalog that provided by the company.
Yeah, could you check, because it is a little bit danger. I need to how to say, use parameters only one paper. I mean, information source is very limited.
Okay, sensei.
But the viscoelastic damper some other companies also produce viscoelastic damper. So we must select appropriate damper.
Okay, sensei.
Okay, sensei.
And also in your thesis, you must mention many references. So otherwise, reviewer will say, "Oh, you decide the damper only from one paper,
Okay,
or one
understand.
researcher. So you didn't do survey
Okay, sensei.
the paper. So could you check another research papers or another product?"
Okay,
Okay, sensei. I will do that.
Yeah, yeah.
Thank you so much.
Okay, Ataya-san, your turn.
Hi, Sensei. May I share this screen?
Yeah.
Since I modeled this frame model like this, it's the y direction is 15 meter and the x direction is 18 meters. And it's 7th floor. And I choose two type of column from 1st to 4th floor. This is the properties, and from the 5th to 7th, this is the properties. After analysis of TMD under 4 earthquakes, under El Centro, just the 1st floor yielded.
Why?
Under
Why first floor is yielding?
Because it's not as much as strong to yield, Sensei.
Usually you design the building, to yield at the beams. Weak beam, strong column design.
Yeah, but because the floors are rigid, 2D rigid, Sensei. Otherwise,
rigid, you assume 2D rigid or 3D?
2D rigid, Sensei.
2D?
Yeah,
so
Sensei, 2D rigid.
Deformed. But it looks beam is not deformed.
In 2 rigid, I don't know, maybe beam doesn't work, I think. Don't deform, Sensei.
Could you open Stella? You can run on the screen.
Okay, Sensei.
And could you click option member? So mixed floor, okay. And
these floors are too rigid. Rigid.
Too rigid.
Yes. All of them, Sensei.
All of them. So
yes.
There is no TMD right now.
Yeah, right now there's no TMD.
Yeah, okay. And could you push over?
This model?
Yeah. No, don't put the capacity. Number 1 is okay.
Okay.
Yeah. Oh. Strange. How about the fast mode? mode 1. Could you start moving? Could you amplify? It's not so. Okay. How about second mode? Okay. Could you stop and show me option structure?
What, Sensei?
Option structure. Option. Yeah. This,
Yes, Sensei.
you allow only one
Only this direction. Yes,
horizontal direction.
Yes, and
No rotation.
yes, because I think it is so maybe say unstable, but at the first I didn't try to release all of them or 3 of them. Just I tried to work on one direction, Sensei.
So how about 2, 4, 6, 7? X direction only. Could you do it now?
Uh, 4, 6, 7.
It is written here. 2, 4, 6, 7.
Yes.
Not 2, 3, 8. 2, 4, 6, 7. Yeah. Right, again. Push over. You don't need to touch, just the static and click start. No. Okay. It's working. Going down. Some column design is probably shear yielding happens in the column.
Without TMD Sensei, if we put TMD, maybe it doesn't work. I don't know. Just I remember that once I tried with Saranya-san.
I don't think so. So TMD, you put the rigid floor only
for
TMD?
Yeah, this model is to install TMD, but the floor that TMD is installed, that floor have to be flexible, otherwise the TMD don't work. Yeah.
Flexible, but you can put rigid, right?
Yeah, other floors are all rigid, 2D rigid.
I don't know. Do you have a model of building with TMD?
Yes, Sensei.
You use this one. Okay. Check option structure. And change 2, 4, 6, 7. Okay. And could you click floor? Yeah. And F1.
The floors are 2D rigid.
Okay. And I want to see the floor of TMD.
This is flexible.
Yeah. And could you rigid? You use old version. Use new version of Stella.
It's 3. 11.3.
Again, you please download.
Okay, Sensei.
Latest one. Could you download it now? Oh, it's a Japanese version. So could you? Okay. Now but
No, it's
still a
Japanese.
3DJ.
It is Japanese sensei. So
You automatically translate. Okay, it's okay. Could you go down? Yeah. This is one in English. Oh. Okay. Okay, could you click option structure? Okay, and please insert. No. Use it, but only horizontal direction. So please put this number 3, 4, 5, 6, 7, 8. Yeah. Okay. Now please try to run. Could you click fast mode? TMD is moving? It's how about second mode? Second. Okay. Yeah, it looks working. Yeah, okay.
for the first mode, it doesn't think.
No, it's moving together.
Difficult to recognize.
Yeah, but when you click second mode, sorry, I have control. もしもし。Yeah, bien. Okay, could you, so is it okay now?
Yes, Sensei, it's okay.
Yeah.
Uh,
Solved.
yes, maybe I will check this analyze based on this, Sensei.
Yeah.
But if it was wrong, the model that I analyzed before and I showed that all floors are rigid and just only the TMD.
Yeah. So this model is not good.
Okay.
So next time, please show me again.
Okay, Sensei, but maybe I have a very quick to that what I have done. And this is based on the other, based on the previous calculation I calculated for single TMD and multiple TMD, which is 2, like this, Sensei. So it reduced the displacement, and on just for Tohoku and Kobe, the first floor failed.
Okay. So we cannot believe this without the model is wrong. So
okay, Sensei.
Please do same thing for new model.
Okay, Sensei.
Yeah. So it's okay. So is there anybody who wants Sarayan-san? How about you?
No, Sensei, I don't have anything to show.
Okay. So shall we discuss next meeting? So today is 28. Yeah, control group. So how about Monday, 10 July? Same time, 3 o'clock.
Okay, Sensei.
Okay. Yeah. Okay, so the next meeting will be Monday, 10th of July, 3 o'clock. And so Zafira-san, please send me the model.
Okay, Sensei.
Okay, so shall we finish? Yeah.
Thank you very much. Majima, when is the deadline for the paper submission? Yokohama, the GESS.
August 15.
August 15. Okay. Just now he asked when is the deadline for paper, and I said August. Oh, we have one more. Let's discuss more.
I already finished.
I'm so tired. Never ending discussion. I should just say tomorrow, Sensei.